Welcome to our Sonar webinar entitled Finding the Bad Apple in Your Regular Expressions, where we will demonstrate some common mistakes which can occur whilst writing regular expressions. We'll show you how Sonar can detect problematic expressions, plus give you techniques to improve your regular expression performance. I'm Andrew Osborne, your moderator for this webinar, which will be presented by Johan Belaites. Please allow me to very quickly go over the essential housekeeping points before we start. The session will last 30 minutes, and we will include a Q&A at the end. You are invited to submit your questions via the Q&A box in Zoom during the session, not via the chat box, so via the Q&A box. And we have two panelists standing by, Sebastian Hungerecker and Joe Tingsan-Charlie from our R&D and support teams, respectively. They are tasked with answering as many of your questions live during the webinar. This session will be recorded, and we will send out a link via email in the coming days. Finally, at the end of this webinar, a short survey will pop up on your screen. We consider your feedback to be a gift, so thank you in advance for your participation. So without further ado, I'd like to introduce to you today's presenter, Johan Belaites. Johan is a Java Kotlin software engineer at Sonar, part of the team developing static code analyzers for Java and Kotlin, as well as Scala, Ruby, Go, and Apex. He was a core contributor to the SAST engine developed by RIPS Technologies and integration of said engine into the Sonar products. He received a BA in computer science from the University of Cambridge and an MSc in IT security from the Ruhr Universität Bochum. Johan, over to you.
Thank you, Andrew. Yes, so let's talk a little bit about some of the problems we have with regular expressions nowadays. And for that, I'd like to start with a little bit of motivation or background. So there have been a couple of high-profile outages in the last few years. So Stack Overflow and Cloudflare both went down for around half an hour in 2016 and 19, respectively. And both those outages could be traced back to the same core problem, which was a RDoS issue, or regular expression denial of service. It's also referred to as runaway regular expressions or catastrophic backtracking. I'll refer to it as catastrophic backtracking for the rest of this talk mainly. So in fact, apart from this, there is many other problems still present today. We have CVEs as recently as 2022. And so at Sonar, we started looking at this problem of regular expressions being in the static code analysis world and writing tools for that 2 years ago, and did some work into it, which I would like to talk a little bit about today. So I want to go into particular catastrophic backtracking as one of the issues you can have with regular expressions into a little bit more depth. We can't fully go into the entirety of the depth, but there's a lot of nice online reading about it as well. And then I'll briefly cover a few other areas of issues in regular expressions as well. So let's talk about this catastrophic backtracking. And to understand catastrophic backtracking, we need to know what backtracking is, first of all. And backtracking is a technique used by many regular expression engines, not all of them, but many, to well, match input strings and provide certain features to the developer to match those input strings. I'll give you an example in just a moment, but essentially what it is the regular expression engine can sometimes choose different sub-expressions of a regex to match a certain character in the input or a certain series of characters. And it can make a decision on which sub-expression to use, and will try one or the other. And then later on, if it cannot find a match for this input string, it'll try the other option, backtracking some decisions it made afterwards. So we'll see an example in a minute. When we talk about catastrophic backtracking, we talk about backtracking that causes the engine to well, backtrack so many times and do so many steps that in fact the number of steps that the engine needs to take to try to generate a match for the input becomes super linear. So it's anywhere between quadratic time or even as bad as an exponential number of steps given the input length n, which of course, as we all know, is not great to have exponential anything in your code in most cases. So I want to take a little example here, example regular expression. Imagine I want to match email domains. I'm going to ignore everything that comes before the for the moment. And I'm going to try to match only email domains that end in edu and ACUK. Let's assume I want to filter out students from the UK and the US for some student-focused program. And I'm going to show you how this regular expression would match this input we saw before. For that, I have transformed this regular expression into a little graph of how it functions. And you can read the slide from left to right, and we'll step through it step by step. I do merge and skip a few steps. The real regular expression engines do this really character by character. We'll merge a little bit to be slightly faster. So we have this input, this at cam.ac.uk. And of course, the first character, the at character, simply matches one-to-one. We have an at in the regular expression, corresponds to the at in the input, all good. Then we get to the next sub-expression in this regex, which is this dot asterisk question mark. And essentially what that is, the dot is an any character wildcard, so it matches pretty much any character. The asterisk is a quantifier or a repetition, and it says that this any character wildcard can be repeated 0 or more times, with a question mark making that quantifier a lazy or non-greedy quantifier. And what that means is that the engine will only use this wildcard if it has to. If it can match the character in some other way, it'll do that. So in this case, we encounter the C, the A, the M of cam in the input, as seen at the bottom here. And all those letters can only be matched by this wildcard, until we get to the dot. And this dot, in fact, could be matched by the wildcard, but it can also be matched by this slash dot, which is a dot literal. So the engine will prefer to match it with a dot literal, since we have this question mark as a non-greedy quantifier, and it'll do that. And all is good. Essentially, I'm skipping a few steps here, but eventually we'll find this ac.uk at the end, and we match the entire input. It takes around 30 to 40 steps, depending on the engine and depending on how exactly you count. Just keep in mind that order of magnitude for later. So all good there. What happens if we have a slightly less expected input? So here I have a malformed input and I've not properly thought about it as a developer. So it fails, which is correct because it ends in com and not an ed or ac.uk, but it takes over 200,000 steps for that. Now, remember, it was 30 to 40 steps that we required earlier to match this valid input. And so this is a huge change in size in terms of how many steps this engine requires to find out that, in fact, the input is not matching. So how come? Well, the at, of course, is still a match as the at. But what happens if we encounter all these dots? So it's 14 dots total. And we saw earlier that, in fact, since we have this question mark in the regular expression that makes the quantifier of that's attached to the wildcard non-greedy, the engine will actually prefer matching dots with this dot literal. And then it will take this, this plus is a quantifier that means once or more, it's also a repetition. And then it will basically just do 14 dot literals to match those 14 dots in the input. That's fine, that it can do that. And then it moves on to the next sub-expression in the regular expression, which is the edu or ACUK, which of course does match because E or the A of edu and ACUK does not match the C of .com. All right, so at this stage is where the backtracking happens. And this is an example of backtracking. The engine can't proceed, so it has to go backwards. It has to change some decisions that it made earlier. So what it does is it looks at the characters it had matched before with this dot literal and sees, okay, so the last character, in fact, it has to match with the dot literal. There's no choice. But then the second to last dot, it could also match with the wildcard. We didn't do that earlier because it's a non-greedy quantifier attached to the wildcard, but that doesn't mean it wouldn't be possible. So in fact, the engine tries that. It'll use the NA character wildcard and then the dot literal just and to basically summarize that we have two different ways of matching those two last dots, right? Two dot literals or wildcard and the dot literal. Obviously, once we proceed to the POM, we'll still fail because the E and the A still don't match the C. And we as humans can already see this is never going to succeed because E and A will never match C, and then this is not going to change. A lot of regular expression engines don't have this kind of oversight, and they'll just try every possible way of generating a match, no matter what, essentially. And of course, there's some optimization in some engines, but generally speaking, this is a danger in many engines. So it'll backtrack one more character. It has tried the last two already. It'll backtrack to the third to last dot. Again, it can choose to match it with a wildcard instead of the dot literal, adding two more different ways of matching those three dots in the end. So in total, to match those three dots in the end, we have four different ways. The two we just tried before, and now two more by changing the decision we make for the third to last dot. Still, the E and the A won't match the C, of course, so we backtrack once more. We have four dots. 4 dots can be matched in a total of, well, 2 times 2 times 2, so 8 different ways. And you can already see where this is going. To match the entire 14 dot sequence, the engine actually has a huge number of possibilities of matching those by choosing either whether it wants to match each individual dot with a dot literal or with a wildcard. So a total of 2 to the n-1 in this case, and 2 to the 13 different ways, which of course is an exponential amount of different ways to match it. Now imagine every time the engine tries to generate a match, it takes, let's say, 30 to 40 steps, and voila, you're at over 200,000 steps. So this is an issue in terms of performance. It could take down your service in some rare circumstances, as we saw with the Cloudflare and Stack Overflow examples. In most cases, it'll probably just be a bit slow. In many cases, it won't immediately take down your service. Still not great. Of course, there's a lot of other issues we experience when we write regular expressions. I think most of us will not disagree with that. And essentially the same sort of problems that affect regular code that we develop in any other language also affect regular expressions. So we have issues with readability. A lot of times we have unnecessary complexity in regular expressions, often because we don't understand features properly, or because there are ways to make things more concise that we don't know about, because the expression has grown over time. Many reasons, right? There are very regex specific or regex feature specific misunderstandings and problems we can introduce, such as we have duplicate characters in character classes or empty character classes, for instance, leading to potentially behavior that is different to what we expect when we look at the regex, or maybe it's just a little bit less readable in either case. Logical errors are easy to introduce. All kinds of things. We can have impossible back references. We just matching or not matching certain things where we didn't expect our regex to behave that way. We're dealing with text here and with parsing text. Of course, Unicode is an issue. It depends on the engine. Some engines have more support for Unicode, some have less support for Unicode. In Java, for instance, to make the case insensitivity work properly, you have to pass the regex engine a specific flag to also consider Unicode characters. Otherwise, they wouldn't be considered by default. So a lot of other edge cases that we can also encounter, of course. All in all, it's a lot to keep in mind for maybe you just writing a quick regex expression to do a task. So, okay, so we have all these problems, and at Sonar, we're in the world of, well, static code analysis and writing analyzers for all kinds of different languages. And there isn't much good static analysis of regular expressions, well, automatic static analysis out there. So we thought, okay, let's see if we can do something about it. And so a couple of years ago, we started developing a new regex analyzer. And it's based on non-atomistic finite automata, which, if you're not familiar with an NFA, it's essentially the little images, the little graphs that we saw earlier when we went through the regular expression, how it matches the input, and the graph of state nodes with some edges in between. That's essentially the NFA for that regular expression. It's based on a couple of papers here. You can look at those in your own time. And that's kind of the core of the engine. We generate the NFA from a regex we find in the code, and then we can analyze that NFA for certain patterns that indicate that we have issues in those categories that we saw earlier. I'll give you one example, the example of the catastrophic backtracking, the exponential catastrophic backtracking that we saw with the 14 dots. And here we're looking for a pattern of intersecting loop execution paths. And what do I mean by that? So take this example here. This regular expression, it's a repetition. So we have a little plus here, which means it's repeated once or more, of an A or a word character. The \W is a word character class. Now this word character class already includes, amongst other things, a lowercase a. So every time the engine encounters that A in the input, it can choose whether it wants to match that A with the A in the regex or with the word character class. So essentially, if we have 3 A's in the input, we can match it in 2 to the 3, so 8 different ways by combining the A and the word character class in any way we want. And so essentially, we have different executions of that repetition, or if you will, you can unroll that loop or that repetition in different ways by making a different decision in each of those iterations, while still matching the same input. So all those executions or unrollments of that loop are intersecting, because they intersect in that they match the same input. And once we detect a pattern like that in the NFA, we know, okay, there's some catastrophic backtracking here. So there are some limitations to this approach. They don't lend themselves well to some of the more advanced regex features, such as lookarounds. They can be exponentially complex to analyze with this approach. However, and we have an intern who's currently doing some research in this, their simple cases are probably supportable. They're not yet, but they might come in the future. Also difficult are back references, because they actually result in regular expressions being able to match more than just regular languages, and they can match also context-free and context-sensitive languages, which are also not very well suited to be represented by non-deterministic finite automata. Again, it's something we could probably build in some rudimentary support, and we may do in the future. The nice thing about this approach is, though, that we can really see, well, once we identify a pattern, we can map it back to the regex and exactly where in that regex the problem is to flag that to the user or to the developer. So then let's talk about a couple of generic tips on how you can avoid some of these issues, and especially the catastrophic backtracking and also some other issues. Particularly for catastrophic backtracking, if you don't use a backtracking regex engine, and there are algorithms out there that don't use backtracking, you can't catastrophically backtrack, obviously. It does change the feature set that the engine provides a bit in most cases, but it might be an option depending on use case. You can use possessive quantifiers. I'm not going to go into too much detail. If you're unfamiliar with possessive quantifiers, maybe worth reading up on. Quick summary, essentially there's 3 types of quantifiers in many regex engines. Greedy is the default, non-greedy is with the question mark afterwards that we saw earlier, and both those allow the engine to backtrack and to kind of change the behavior, that the matching behavior, if there's an alternative to using the expression that is preceding the quantifier. There's also possessive quantifiers in many engines, which essentially forbid the engine from backtracking. And so, of course, if the engine is not allowed to backtrack, it can't catastrophically backtrack, although that also changes the logic of your regex slightly. And I know that some regex engines don't support this. The .NET regex engine, for instance, doesn't have native support for possessive quantifiers, with some ways to emulate it. But anyway, not going into too much detail here. Generally speaking, be cautious if you find you're using intersecting sub-expressions. So that is different sub-expressions in a regex that can match the same input. So think of an A and a word character class, for instance. If the engine can choose which one to use, that could be dangerous. There are valid use cases, of course. Similar with nested quantifiers, it's a repetition inside of a repetition. So it could be dangerous if the engine can choose different paths. And it's also a bit harder to understand if you have nested repetitions, what the regex can actually match. Generally speaking, if you use, or if you try to match single characters, try to use character classes instead of alternatives if you can. So use the one on the left here, because as soon as you have an alternative, the regex engine can try both. And here the interesting part is that underscore is actually also contained in the word character class already, which might not always be obvious. If you use a character class, it's essentially treated as a set and it won't try it twice. Of course, even better, don't have duplicates in character classes at all. Just use the, in this case, word character class. And these, the fact that you could transform them to simpler or more efficient constructs or sub-expressions, there's where static analysis can really help you, because those rules are encoded. Some of those rules are encoded in static analysis. So a little example. I wonder if you can see a problem with this regex. And obviously that's a trick question, because if I ask you, then there is a problem or a couple of problems. So already we can see so we have three alternatives here. We have A to Z or underscore or a dot literal. Repeat it once or more times. And so there's a couple of problems here. First of all, we're trying to match character to character. So generally speaking, we should use a character class. And in this particular case, it's even worse, because notice how we have capital A through to lowercase z. Subtle difference, I know, but it is there. And in fact, that includes all characters ranging in the ASCII range from capital A to lowercase z, which includes all capital and lowercase letters, and a couple of special symbols, such as underscore. So we have an alternative of underscore or a character class that includes underscore, which can lead to catastrophic backtracking in the worst case. And again, of course, even better, please don't use character ranges with capital and lowercase letters mixed. More explicit, of course, is something like the ones down here. All right, so this is the example that brought down Cloudflare. Already you can see it's starting to get slightly more complicated, maybe hard to find an issue immediately. And the nice thing is when we build an NFA, we can analyze it part by part and find those patterns, no matter how complex the rest of the regex is, or more or less no matter. In fact, here at the very end, we have several repetitions in a row of a wildcard character. And so every time the engine can essentially choose which of those repetitions to use, more or less. And that can lead to catastrophic backtracking, so much so that it caused a nearly half-an-hour outage for Cloudflare. So there is a lot of crazy regular expressions out there. This is just an example, which probably has many issues. It's actually a regex to match email addresses. So just as a reminder, you can write very complicated regular expressions to do seemingly simple things. Maybe ask yourself if that's the best technique or best tool to use in those cases. Some takeaways. I think few people would disagree here. Regular expressions can be quite difficult and hard to read and maintain in many cases, especially as they get longer and, well, older. A lot of times when we do write regular expressions, it's with what we are trying to match in mind. We often don't really consider what we don't want to match as much, and also a lot of edge cases, of course, are hard to consider. So trying to consider the non-matching case or the edge case slightly more, well, it can't harm, of course. Regex features behave differently than expected due to the developer simply not being familiar with the feature enough, or also the Regex engine implementation doing something different than maybe what the developer's used to, or a different engine implementation that he's used to. So that's something to be wary of. Know which engine you're writing your regular expressions for. And finally, of course, if you can, use static code analysis. So at Sonar, we do have this regular expression engine available now. It's open source and free to use. And in fact, the nice thing is we've been able to find some bugs in our own regular expressions that in our own products using our analyzer. So in fact, even the people here who have researched a lot about this topic and are now quite in depth still make some of these mistakes, and using static analysis helps us as well. So special thanks here goes out to Sebastian Hungerecker, who is here in the call with us today, who kind of kicked off this whole engine, or this whole analyzer project, as well as the Sonar languages team, which then invested in the last 2 years to bring this engine to various different languages. There's some references at the end if you want to have a look later. Yep. Otherwise, I'll give back to Andrew.
Excellent. Thank you so much, Johan. That was great. As we move into a short time of Q&A now, please do put any last-minute questions in the Q&A box, and I will gather those. I just wanted to briefly share, whilst you're doing that we have some upcoming webinars on your screen for the Sonar Cube LTS, our long-term support webinars. So I do invite you to register now for the session that's most convenient for you. There should be a link in the chat as we speak. Right, on to a few questions, if I may, Johan. The first question, how would you handle user-provided regular expressions, so at runtime, with this context in mind?
Yeah, so of course, if you have user-provided regular expressions, you can't verify them very easily if they contain dangerous sub-expressions, or if they contain something that is vulnerable to redos, regular expression denial of service. So even if you can do some static analysis, it's always a risk something slips through. I think you have to use a timeout in the end. You won't get around that. But yeah, user input in the regular expression case, of course, is always slightly more difficult to deal with.
Okay. Catastrophic backtracking. In a nutshell, how do you prevent catastrophic backtracking?
So, I mean, there is several techniques that I kind of mentioned. In a nutshell, it's probably hard to say because it depends on your regex. Using a static code analysis tool can help you detect some of those issues. But of course, how you fix them depends on your particular situation, and those approaches mentioned earlier can be some of them.
Great.
Not sure if this, yeah.
Yep, I'll just move us on quickly because I've got quite a few questions I wanted to try and get to you. Which languages does Sonar provide rules for regular expressions?
So we have quite a few languages in general that we provide regular expressions support for. The more advanced support that is based on techniques like this one is, I think it's Java, Kotlin, PHP, Python, I think JSTS pretty much. I'm not forgetting anything. Yeah.
Yep. And which regex engine can I use that does not suffer from catastrophic backtracking?
So there's many regex engine solution out there. It depends on the language you're using, of course, and the environment you have. There is Google's RE2, which I believe doesn't use backtracking. So that's something you could look into, for example.
Excellent. Johan, thank you. Thank you so much. And thank you to everybody who have posed questions. Sorry we didn't get time to cover them all live, but our community is a great place to pose those questions and also review those previously asked and responded to in the past. So once again, thank you, Johan, and thank you all to those who've attended today. Please do visit sonarsource.com for further information on how to clean as you code, and also to check out information on our future webinars and events. And finally, thank you again for providing your feedback via the survey that will shortly pop up on your screen. See you all soon. Thank you.